Welcome, researchers, to The Explainer. Okay, let's dive right into a seriously fascinating topic today. We're going to unpack the 3D mechanisms of copper self-annealing. Now, for those of us working in advanced metallurgy, you know exactly how absolutely crucial it is to bridge that gap between raw, two-dimensional data and a true, deep, volumetric understanding. So today, we're exploring the precise structural dynamics of electrolytic tough-pitch copper, and we're going to fundamentally shift how we've used spontaneous room temperature recrystallization. It's going to be a great one.
Here is our quick roadmap for the session. First, we'll look at 2D limits and 3D needs. Second, the experimental methodology. Third, the principles of PSN. Fourth, CSRX versus DSRX. And finally, we'll wrap up with the conclusions of the 3D volumetric analysis. Let's get to it.
Section 1. 2D limits and 3D needs. So, as researchers, we really have to ask ourselves, why does traditional 2D electron backscatter diffraction, good old 2D EBSD, fail so hard at capturing the true morphology of the particle deformation zone? I mean, for decades, we've relied on these flat cross-sections. But when you're dealing with localized strain fields wrapped around complex 3D particles, a single slice simply doesn't tell the whole story.
The crucial takeaway here is that 3D EBSD is a total game changer. While 2D EBSD gives us really limited through-thickness data and completely misses the three-dimensional morphology of those deformation zones, 3D EBSD accurately maps orientation gradients across all three spatial axes. It isolates the exact size, morphology, and crystallographic influence of rigid cuprous oxide inclusions. Basically, it allows us to map complete nucleation kinetics that 2D methods fundamentally obscure.
Just look at this blue spherical representation. It immediately demonstrates the severe spatial limitations of a single 2D plane cutting through a volume. Look at that grid on the left. If your 2D slice only cuts through the very top or bottom of a nucleated grain, or, worse, misses the adjacent rigid particle entirely, your stereological assumptions are instantly skewed. The 3D volumetric resolution on the right is exactly what we need to actually see the stored energy distribution across the X, Y, and Z axes.
Moving right along to Section 2. Our 3D reconstruction experimental methodology. To forge the high-energy matrix required for the study, the copper really had to be pushed to its limits. The process kicks off with annealing the ETP-copper at 350 degrees Celsius for 4 hours, followed by an 8-minute immersion in liquid nitrogen per pass. Finally, the material undergoes severe cryogenic rolling down to an 80% thickness reduction. This massive deformation at cryogenic temperatures practically freezes dynamic recovery, storing an immense amount of deformation energy that will ultimately drive spontaneous room temperature self-annealing.
Now check out this rigorous 63-hour data acquisition pipeline. Turning those physical samples into a highly resolved digital volume is no small feat. The team used a plasma-focused ion beam scanning electron microscope to carefully mill away 100 nanometer slices. They captured 150 sequential 2D slices in total, and then computationally cropped and rendered them into a precise 14 by 14 by 3.75 cubic micrometer volume using Dream 3D. It's a really brilliant workflow. And here's how that builds our digital reality. You can clearly see the raw, stacked slices on the left. The absolutely critical step here is aligning these sequential slices to correct for any FIB milling misorientations. The researchers didn't mess around. They used strict thresholds, requiring a confidence index greater than 0.1 and an image quality above 50, just to ensure the crystallographic data was absolutely pristine before doing any volume rendering.
Okay, Section 3. Principles of particle-stimulated nucleation. At the very heart of this explainer is particle-stimulated nucleation, or as it's known in Korean academic circles, Sengsung. These non-deformable hard copper oxide particles survive the cryo-rolling process totally intact because they literally don't deform with the ductile copper matrix. They act as rigid barriers and critical stress concentrators. This forces an extreme localized strain field, what we call the particle deformation zone, which then dictates the exact specific nucleation sites of new, fine grains.
Take a close look at those cyan cuprous oxide particles on the right. 3D EBSD mapping lets us see the exact spatial relationship between the catalyst and the new grains. Line profiles from the source data reveal crazy high lattice curvature right here. Intragranular misorientation reaches a massive 24 degrees immediately adjacent to these particles, compared to just 14 degrees out in the particle-free zones. That localized energy peak, that is exactly what triggers Sengsung.
Let's shift gears to Section 4. CSRX and DSRX recrystallization.
This diagnostic matrix provides a crystal-clear mental model of the dual nature of room temperature self-annealing. It's like a balancing act. On one hand, we have continuous static recrystallization, or CSRX. This is the dominant recovery-led pathway driven by a moderate stored energy differential. On the other hand, we have discontinuous static recrystallization, or DSRX. This is the minority pathway, and it requires a super high local stored energy differential, characterized by strain-free nucleation and distinctly low kernel average misorientation, or CAM signatures.
Since external thermal energy is completely absent during room temperature self-annealing, the driving force is inherently pretty limited. Consequently, the microstructure relies heavily on the dominant CSRX pathway you see mapped out here. Small differences in stored energy drive progressive subgrain rotations. Notice the low-angle grain boundaries marked in red? They're gradually accumulating dislocations and rotating to increase boundary misorientation beyond that 10 to 15 degree mark, eventually maturing into the high-angle grain boundaries marked in blue.
Conversely, check out the blue arrows pointing to those isolated pockets. These are the zones of extreme energy differentials, where DSRX completely takes over. Here, new nuclei grow super fast, physically consuming the surrounding dense dislocation networks. The end result? Pristine, entirely distinct, strain-free grains that have crystallographic orientations completely diverging from the parent deformed copper matrix.
And finally, Section 5, Conclusions of our 3D volumetric analysis.
Through some really careful digital masking of the cuprous oxide particles in the 3D rendering, stereological measurements were able to isolate the newly nucleated grains. The data confirms that the representative volume of a single newly nucleated PSN grain is precisely 0.23 cubic micrometers, and it exhibits this fine, equiaxed morphology that's highly characteristic of rapid stored energy release.
Now, if you're wondering about the accuracy of these volumes, check out this stereological validation. The researchers actually tracked a large particle as it emerged and vanished across sequential 2D slices. The maximum area observed in 2D gave a derived diameter of 1.69 micrometers. When they compared that to the 3D volumetric back-calculated diameter of 1.77 micrometers, well, that incredibly tight correlation definitively proves the high fidelity of the FIB, serial sectioning, and alignment protocol they used. It's spot on.
So, to summarize our whole synthesis framework today, non-deformable catalysts force extreme localized strain, and that leads to a concurrent, highly heterogeneous room temperature self-annealing response. Coarse particles, specifically those larger than 1.5 micrometers, are highly efficient for this. We now know definitively that room temperature self-annealing is not some monolithic event. Actually, CSRX and DSRX operate concurrently side by side, generating a really complex matrix of strain-free grains alongside active subgrain recovery zones. I want to leave you with this final, provocative thought to spark your future academic exploration. By truly understanding and mapping the 3D mechanics of particle-stimulated nucleation, how can we intentionally manipulate these non-deformable particles to engineer advanced, highly conductive metallurgical designs with customized grain structures? The 3D frontier is wide open, and the data is waiting for us. Thank you so much for joining me on this explainer, and keep pushing the boundaries of your research.